Hi, welcome all to the 22nd seminar of the in the seminar series. Today we have speaker Mr. Shibotosh Biswas from Space Physics Laboratory. Shibotosh completed his bachelor's and master's from University of Calcutta, and then he joined a Space Physics Laboratory as a junior research fellow. He is currently in the third year of his PhD, and he is working under Dr. Ankush Bhaskar, and his specific area of research is on magnetic reconnection processes on the Earth's magnetosphere. And today, the speaker will be talking on the magnetic reconnection, a gateway to understanding the explosive plasma events. The speaker prefer to ask the question towards the end of the seminar, so audience can keep their questions, note their questions towards the end, and then we will discuss. So over to the speaker.
Okay. Thank you, Govind. Can you just check once whether I am audible and visible?
Yeah, you are visible. You are visible and audible.
Okay. So thank you, Govind, first of all, for the nice introduction. And I want to thank Indus to give me an excellent opportunity to present myself in this community, in front of this community. So before starting, I want to say that my home is just in between a railway track and a road, so you might hear some noises. So please excuse me for that. Okay, so well, today I'm going to discuss about a plasma physics process as a fundamental physics process called magnetic reconnection. Well, first of all, I want to start with a beautiful poem I got from a small book called An Introduction to Physics of Plasma, Fourth State of Matter by Eliezer and Eliezer. So I want to read it for you. It says that in the beginning there was nothing at all except for the universe compressed in a ball. Then followed the Big Bang episode, causing the ball to violently explode, creating entirely a hot plasma lather, which was actually the first state of matter. And after the explosion, the matter cools down, turning the fragments into stars, just like our sun. And during the expansion of this gigantic heat storm, matter cooled down to gas form. And the cooling continued to liquid and solid formation to form different matter configurations. So in the beginning, with the coming of civilization, prehistoric man's first inauguration was to the earth and rocks and the rain and water. These solids and liquid became the first and second state of matter. And the gas was realized later and became the third phase. And last came the plasma to interchange from the first to the fourth place. Well, you know, our Earth has an atmospheric system, right? And if you go a certain height after that, it was in a plasma state, right? There are electrons and ions. We call it as an ionosphere. So whether you are studying the ionosphere and go up to that, there is a magnetic field surrounding our atmosphere. It's called magnetosphere. So whether you are studying ionosphere, magnetosphere, and then go into interplanetary space, it is actually filled with solar wind. That is a magnetized plasma that has magnetic fields. You go on to solar physics. The sun is a ball of plasma. All the phenomena that we are now observing is a plasma physics phenomenon. And then you even go beyond to that, to the heliosphere. The sun's influence is kind of a spherical shell kind of thing, where only the sun's magnetic field is the main driver of that, and it separates us from the interstellar space. And even beyond, if you go to the interstellar space, to astrophysics, observational astronomy, one common state of matter that we have to read about or have to have idea, that is called a plasma state. And it is the fourth state of matter. What if you want to define the plasma in a very short and general way, we used to say that, okay, if we have a gaseous system and you keep impinging energy into that, then one time it will come, the electrons from the atoms will come out. They have a sufficient ionization energy. It will come out, and then it will be an equilibrium situation of electrons and ions. So that is called a plasma system. It's a very general, it's not a bookish kind of definition. It's a general definition. So in a plasma, we have charged particles. They are roaming around, electrons and ions. And once you have electrons and ions in a plasma system, you think of it, we have all studied from our basics or BScs, MScs, and even beyond that. Like if you have charge particle motion, then it will create magnetic fields, and static charges create electrostatic fields. So the full plasma system not only have electrons and ions within it, it also have fields like electric and magnetic fields. So the magnetic field is one of the interesting subject for research. Means from the time it was discovered, the magnetism, then magnetic material, people are very much interested in magnetic things and magnetic material and all the magnetic phenomena, right? Nowadays, in our nature, we used to find these magnetic fields in various scales. So to start with, if you go to the fundamental scale of our nature, like fundamental particles like electrons, okay? So these electrons are actually tiny magnets. They have some quantum angular momentum, and because of that, they have tiny magnetic fields. Now you come to our day-to-day life. We have bar magnets. We have some instruments which are magnetically operated. So these are all our surroundings. We can see these magnetic fields, right? And then you just scale up a little bit further. We have our own planet, our Earth, that has its own magnetic field because of some phenomena that is happening at the core. And the core itself is actually made up of plasma, molten irons, nickels, etc. So it creates a magnetic field surrounding to our Mother Earth. And then you further scale up to the interplanetary space. We have solar wind, continuous flow of plasma from the sun that also carries magnetic fields. And then you go to the sun, solar physics. Sun itself has a dynamic magnetic field structures. It's not modeled by a normal dipolar field. It's a very complex magnetic structure. Here I have mentioned a cartoon picture for that. And usually the average magnetic intensity is kind of 1 Gauss. And then this is up to sun. And then if you go beyond that, beyond our heliosphere to interstellar space, there are neutron stars which have magnetic field, which are neutrons that are rotating very fast, and specific kind of that star is called magnetars. They have their own magnetic field that are very, very strong. And not that is the end. Even you go beyond that, our galaxies, these are huge structures, right? They also possess galactic magnetic fields. So what I'm trying to say is this magnetic field is actually a ubiquitous element throughout our universe in all scales and different intensities. So generally we have a tendency to think about and to research on magnetic fields. Well, now today what we are going to discuss is a magnetic phenomena in a plasma. So our basic system is a plasma. Plasma has electrons and ions that I already told, and have magnetic fields also. Now we are going to talk about 2 different processes. And the second one will be our further, I will elaborate on that. So, okay, so we have a plasma system, we have magnetic fields. Okay, so now you can think of these charged particles are moving all over the system, and that creates small scale magnetic fields. Yes, that are also interesting things if you wanted to research on, but for a general purpose of our study, which I am basically studying Earth's magnetosphere, or people who are studying solar magnetic field, these are very large scale phenomena. So we have to have a process that can create large scale magnetic fields. One of these processes is the process which creates these large scale magnetic fields is called a dynamo mechanism. This is a plasma process. Suppose you have a plasma system and that has a differential rotation. What does that mean? Because different plasma in a system, different part of the system is moving in a different speed. So they have a relative velocity in between them. So that is called a differential motion of the plasma. If you have that, and if you have some seed magnetic field, small fluctuations, then it can lead to large and big scale magnetic fields. And that is the exact reason because of which we have our Earth's magnetic field. In the core, there are molten plasma, irons, and nickels. Not at the core, at the mantle. And the mantle, because Earth is rotating, and the mantle has a differential rotation. because of that, it generates almost dipolar kind of magnetic field structure that extends very far away from Earth. In the day side, I'll come to that picture after some slides. There is a certain diagram or some structure of magnetosphere. So it's the main point is it's a large scale magnetic field. And what is happening if you want to know the dynamo mechanism, the mechanical energy, because the mantle has a plasma, it is moving, so it is a mechanical energy. It is converted to electromagnetic energy in producing the magnetic field. This is a basic fundamental phenomena is happening in dynamo mechanism. I am not going into detail of dynamo mechanism because my topic is a bit different. So this is a generation mechanism of magnetic field. Now, you come to the annihilation process of magnetic fields. Now, there are two distinct processes by which a magnetic field can annihilate in a plasma. One is called diffusion of magnetic fields, and it's a very slow process. Like if you keep a magnetized plasma as it is, then after a certain time the magnetic field tends to diffuse from the plasma. That is called a diffusion of plasma. It happens to every system. There is a certain length, a certain time scale for that diffusion. It's a very slow process. And generally, it turns up that these magnetic energies and things, they tend to convert to heat energies in case of diffusions. And there is another process that is happening very rapidly and explosively. That is called magnetic reconnection process. And we are bothered about this reconnection process. And we, in this talk, will try to understand what is the basic fundamental physics behind the reconnection. So what is the difference between these two processes, diffusion and reconnection? As I told you, diffusion is just you place a system as it is and keep waiting for some time, then plasma, from the plasma, the magnetic field will diffuse out, and in a certain situation, the magnetic energy can turn up to heat. But in reconnection, because it's a rapid process, a non-linear process, and explosive, that means in a short time, huge amount of magnetic energy can convert to particle energy, whether it can be heat or kinetic energy, and often it can lead to particle accelerations. So this process, magnetic reconnection, is our primary concern for today's talk, and we are going to explain the fundamentals of it. So to give you a brief definition of it, reconnection is a universal plasma process. It's a very important thing. It's a plasma process. Without plasma, it cannot happen. I'll tell you why. Plasma process by which the magnetic fields changes their topology. Topology means structure. It changes the topology and release magnetic energy. If you want to grasp these lines, you just think of like this way. These magnetic field lines, they act as rubber bands, okay? And there are plasma, they are controlling the field lines. I'll tell why it is controlling the field line. There is some special phenomena it is there called frozen in conditions or like that. So we have some magnetic field lines and that are controlled by the plasma. So if the plasma is going to some twisting and something like that, then it can twist up the field lines also. So once you twist some rubber band, then what you are doing, you are actually giving some potential energy to the rubber band. And once you remove the external forces or external source of energy, it will come down to its initial initial potential energy situation. So same thing is happening in this case also. So we have a plasma that has some magnetic field, and in some certain situations, these magnetic fields are getting so much of potential energy in it. So once certain situation prevails, it releases its potential energy and come down to a normal state or lower potential energy state. That is a basic fundamental physics concept, right? So what actually happens? Let me just turn out the pointer. Yeah. So if you see this picture I have shown you in A, B, and C, you consider there are two plasma systems that are sitting by each other and they are coming towards each other. And one has a magnetic field V1 and another one has a magnetic field V2. If you place these two plasma side by side, then in between there is a boundary. In that boundary, the two different sides, the magnetic field lines have two different orientations. Now, what will happen there? I will give you an example in normal situation what will happen in the next slide. But here what happens is these two field lines will undergo reconnection, or so to say cutting and pasting. It is not exact term. Cutting and pasting should not happen, because cutting and pasting means the field lines are breaking up, and field line breaking up means it's a violation of divergence of B equal to 0. That is a Gauss law, right? So what happens is these two red and blue magnetic fields, they reorient themselves, because these have so much potential energy in it. It reorients such a way that one red magnetic field, it connects to the blue magnetic field line, and same way other in the lower side also. So this is called the reorientation, and in a general sense it is called cutting and pasting, but you should not use that. So this by this reorientation of field line in the boundary layer, what happens is the extra energy that the magnetic field line containing, that we all know that is a B square by 2 mu naught, that is a energy a magnetic field contains. This extra potential energy it releases. Now energy it releases means it should be to different, it should go to different channels. One, with this released energy can heat up the plasma. Some portion of the energy can even accelerate the particles and change the kinetic energy of this surrounding plasma also. So this is a basic phenomena of reconnection. And then if I go to the next slide, so what we have studied up to now is that what is a basic definition of reconnection, and what happens in a plasma system when two plasma comes close to each other and the field lines changes. So now I will tell you very briefly what is the history of this reconnection. It's how people have thought about this situation, right? So there was a person, it was around 1947-48. There was a person called Ronald Giovanelli. He was an Italian person who was working in Australia. So he's actually, this all story started from solar observations. So he was actually researching on solar flares, and he came to a conclusion from some observations that whenever this solar flare happens in some sun has some active regions, we all know about that. These are active regions. Whenever solar flare happens, he found there are observations of neutral points of magnetic fields. Because whenever solar flare is there are neutral points. Then this finding, he then went to his he was actually a postdoc at that time. I'm doing postdoc under Sir Fred Hoyle. He's a famous scientist, famous physicist, and he passed this important observational result to Fred Hoyle, and then he suggested, okay, in solar active region there are solar flares, like flare. In short, you want to say it's electromagnetic energy generation in solar flare. This is a basic thing. I'll tell you that flare model in the next slide also. So Fred Hoyle, he understood that, okay, if there was a magnetic null point in a solar flare system or in some active regions, then there must be some currents inside it. Because if two magnetic field lines are coming side by side, in between there should be some currents that follows from the Maxwell's equation. I will tell you in some next slides. Then he sent this problem, means he told his PhD student James Dunje to think about the problem and come up with some models of that. Then Jim Dunje, he was the main person who named this process as magnetic reconnection, and there was a history behind that. The history is as follows. In our I'll shift my discussion from solar system to ionospheric system, Earth system. In our Earth ionosphere, upper atmosphere, people have observed in the polar regions, North Pole and South Pole, there are some plasma convection patterns. These plasma convections are starting from the day side, it is going to the night side and coming back again. People have different models to explain this phenomena, but they have failed to do so. People do not know why it is happening. At a certain height in the ionospheric level, there are plasma flow patterns. So Jim Dungy, he came to an idea that okay, if in sun two magnetic fields oppositely oriented, they can come and reconnect. Means they can come and explosively means gives rise to energies. Reorientation of energy can happen. Then this can also happen at Earth. So he came up with a brilliant model called the magnetospheric model of Earth. What happens is our Earth has a magnetic field that I have shown you in the previous picture, that the magnetic field line is coming from the southern pole and going to the northern pole geographically. So if you consider from Earth center to the north pole is a positive z axis, then our Earth's magnetic field is actually positively oriented always. Now, as I have told you, sun has all means 24/7. It is radiating. It's giving solar wind that has a magnetic field. So if that magnetic field somehow is negatively oriented, this negative z-axis oriented, then at the day side, our Earth's magnetic field line that is positively oriented and sun's negatively oriented field line, they can reconnect also. They can undergo the same process that is happening in the solar system, that is happening in the sun's corona or sun's atmosphere. And that led to a model called Dungy cycle. It was a cycle for our Earth's magnetosphere. And this is the case. If you see the blue lines, that is our Earth's magnetic field lines, and these yellow lines coming from the sun. And they are undergoing this reconnection process. And due to this solar wind is pushing from the front side, they're taking the field lines to the night side. And again at the night side, these orientations are opposite. And again, this reconnection phenomena is happening. Okay. And because of that, we have this pattern of from day side, the plasma in the ionosphere is going to the night and coming back again. I'm starting this again to just visualize properly. So this is our field line, that is our Earth's field line, and this is the solar wind field line. They are coming close to each other. This is the day side of magnetosphere, and they are reconnecting, going to the night side. Again, at the night side, these two field lines are oppositely oriented, and they are undergoing reconnection again. This is called, one is called day side reconnection, one is called night side reconnection. And because of this night side reconnection, this field line is getting closed and coming towards Earth. And this completes the whole cycle. This is called the Dungy cycle, or another way is, another name is that open field line cycle, open field magnetospheric model. And this reconnection explanation actually fits with the observed pattern in the ionosphere. So that was a beauty of Dungy's proposal. And in the same case, if you go to the solar system, in the solar atmosphere, that is happening at the solar atmosphere also. We have already, all of you have seen this kind of structure of plasma, and these lines are actually the magnetic field lines that plasma carries. And these foot points, if you see these bright points, these are not static points, they are moving. And once, if they come close to each other, then at a certain height, these magnetic field lines are actually oppositely oriented, because from one position it is coming out and one position it is going down. So in these two branches or these two arms, the magnetic field lines are oppositely oriented. And whenever there is a motion of these two foot points, if they come close to each other, then these oppositely oriented field lines can get reconnected. Okay, and this is a basic flare model. And in this reconnection point, this magnetic field, whatever energy it possesses, it bursts out, explodes into different forms of energy. And even it can generate electromagnetic energies like X-rays and so on, EUVs and so on. And sometimes, often, if it is so violent that a chunk of plasma from the sun, it can come out to the interplanetary space. That is called the coronal mass ejection. So the reconnection is thought to be the driving process of flares and coronal mass ejections. Then, after Dungy proposes this phenomena, it means this same phenomena that is occurring in the sun, we can apply to the Earth's case also. And it is similar to all other planetary systems who have their intrinsic magnetic fields. So this fundamental process it can actually explain many explosive events in our solar system. And even if you go to go beyond solar system in different astrophysical settings also, this is a fundamental process that can lead to particle energization. So means explosively and burstly. Means within some few seconds and minute scale, it can dump huge amount of magnetic energy to the plasma kinetic energies and accelerate charge particles. Then it was around 1960s when Dunge proposed that it's a reconnection process, because the reconnection name came from, because the day side of magnetosphere, if you have seen the video, day side of magnetosphere, these field lines are opening up and the night side again connecting back. So that is why Dunge came up with the name called reconnection. The day side is disconnecting and the night side it is reconnecting again. So that is why he called the phenomena as reconnection. And we, the reconnection community and now plasma community, use the word reconnection as it is. Okay, so it was proposed around 1961 and people are not believing in him. People are saying, oh yeah, it can happen, it can be a bullshit thing. But there has to be some mathematical model for that. If you give a mathematical model, then community can accept that. So in 1957-58, a person called Peter Swift, he come up with a mathematical model, a basic mathematical model in the framework of fluid dynamics. Because in a large scale, a plasma acts as a fluid. Even though plasma has electrons and ions, in a fluid approximation, we do not bother about the electrons and ions individually. We take it as a whole system. It is moving, it has some bulk parameters like velocities, fields, densities. These are all bulk parameters, like electrons and ions are kept in the same footing. This is generally called fluid approximation. The whole system has all bulk parameters and we will bother about the whole system itself. So within this fluid approximation, he came up with scaling, so to say, scaling laws and a physical model for that, means mathematical model, so to say. And that is known as Swift-Parker model. But the problem of this model was, the reconnection, how it is different than diffusion. As I have told you, diffusion takes a lot of time. It's a very slow process. The magnetic field is there. It means diffuses from the plasma and dump its energy as a heat, right? So their diffusion time scale is very large. But what observation was giving us information that these explosions in the sun, they are happening in very rapid manner. Within minute scale, it is happening. A huge amount of energy is changing from magnetic energy to kinetic energies. So we cannot explain this phenomena in the diffusion physics. So we need something else. That's why this reconnection problem came, right? So what Swift-Parker gave the model, that model actually failed to explain the rapidness of the process. So usually we define the rapidness, or we calculate the rapidness of reconnection with a term called reconnection rate, by which two flows are coming close to each other. That is called inflow. I just show you this picture. This blue and green plasma, right? Sorry, blue and red, these magnetic fields, that actually is a plasma that are coming close to each other, right? With a velocity called inflow velocity. And after that, once they are reconnected, once they changes their topology, the plasma, what they will do? They will just go to the perpendicular direction. They will shoot up from the perpendicular direction. That will create reconnection outflows that are given by V out. So if you take the ratio of V in by V out, that will give you that reconnection rate, means how fast these two plasma are coming and reconnecting and going out. So the model they Swift and Parker gave, that reconnection rate was so slow, so it was unable to explain the actual observed phenomena. Then there are lots of people came with different models suggesting fast reconnection rate. One of them was Harry Peschek. He told that, okay, there can be some shocks involved in that. And in 1995, Biscam, he just brought this, he just took this problem into a different footing. We are already analyzing this problem in a fluid dynamical scale. he told that, okay, we go deep into that. We go to the kinetic scale. We treat electrons and ions separately. Then what happens? And he was he was able to do a little faster, means able to calculate little faster reconnection rates. That we'll discuss about that first. So today, what we will discuss is this Sweet-Parker model, that how a simple dimensional analysis can give us a flavor of this reconnection process. And then in a single slide, I will try to explain you the kinetic picture of it. Means if we consider electrons and ions separately, then what happens? Okay, let's go to the fundamental physics of this reconnection. Okay, so let us ask us one question. What happens if two anti-parallel magnetic field lines that come close to each other? What will happen? You take this problem in a different way. Suppose we are in ambient medium, like we are sitting like now itself. You have two magnetic, you have two bar magnets, and to opposite polarity, you are facing each other. So what will happen? The magnetic field lines are actually opposite. That was shown like here, one red and one blue, right? But in ambient medium, there is no plasma. In ambient medium, there are no free-flowing charges like electrons and ions. So they just cancels out each other. But when there is a plasma system, it can contain electrons and ions. We all know that. So from Maxwell's equation, we know that whenever there is a curl of B, there should be a current density J, means there should be a current layer between that. So in a plasma system, if you have two oppositely oriented field lines coming close to each other, in between that, you should have a current sheet in 2D, obviously. In two-dimensional, it should be a current sheet. This current sheet orientation should be such that it will be perpendicular to these magnetic fields, because it's a curl of B, and curl of B is equals to, sine theta into n cap. It will be perpendicular to this plane. So once you are pushing these two plasma from upside and downside, that means you are pushing these two magnetic fields, you are making this current sheet very, very thin. Once this current sheet reaches a threshold, then what happens is plasma instabilities comes into the picture. Instabilities grows, non-linear processes comes into the picture. And the plasma sheet, if you see in this big picture, this plasma sheet breaks up into plasmoids or magnetic islands, and the reconnection starts. So this threshold condition, you cannot explain this with fluid dynamical description, because once you go to that scale, because as I told, you have to push it further and further. Once the current sheet is so much thin, then only it can reconnect. Then only it can tear up to different plasmoid systems, and the field lines can reorient. So this scale up to which you have to push, it's very, very small. It is beyond the fluid scale. Then you have to go to the kinetic scales. So what happens is as the current sheet becomes very, very thin, it tears up and the reconnection starts. And whatever the magnetic field is coming from upside and downside, they just connect with each other and go to the outflows. And it takes all the plasma particles like electrons and ions with them, and it creates an outflow jet. Means from surrounding, if you have some observation, you can see these outflow jets are very high in velocities. Okay. So if you want to fill it in terms of equations, let me give an example for that. We all know about the Faraday induction law, that is a curl of E is del P del T. Whenever there is a change in magnetic field, it induces an electric field. And every one of us has known this equation also, that is called J equals to sigma E plus V cross Q. This is the Ohm's law in the different frame. We have studied in our school level J equals to sigma E, but that is in a different frame. So here the point is, or concept is, if you are in a frame by which you are seeing the plasma is moving, then you just transform the frame, means from plasma frame to your frame, by Lorentz transformations. And then you imply the non-relativistic case, because we are not bothered about relativity here. If you do that, you will end up that electric field as seen by your frame will be E plus V cross B, because of the convection of the plasma, there will be an additional electric field that is only seen by you, not in the moving frame. So this extra term V cross B is called convection electric field. This is very important in case of magnetospheric atmospheric physics. So this is the general form of this Ohm's law. Okay. So if you put this electric field equation into this induction equation, you will get an equation that will give you like how magnetic field changes with respect to time. There are two, if you just go through this step by step, you will get these two equations, this single equation with two terms. First term will tell you the magnetic field can change with respect to convection. Is if the fluid itself it is convecting, and if you are measuring a field from a single place, you can see with respect to time the field is changing. The second term will give magnetic diffusion that I already told you. If you just keep the plasma as it is with magnetic field, after a certain time the field will try to diffuse away from the plasma. That has some certain length scales, and magnetic diffusion is very much important whenever there is resistivity in it, because this diffusion coefficient is actually resistivity by V naught. So if in some situation you have high resistivity, then diffusion comes into picture. And what happens in this case? You know, in between, whenever these two field lines are coming, resistivity is so high, so that this first term, curl of V cross B, the convection term, means if you take the ratio of that, the resistive term will be so high that the equation turns up to a diffusion equation, and the field lines try to diffuse. So whenever there is a resistivity in a system, reconnection or diffusion, this sort of phenomena comes into the picture. Okay. So now this is a steady state model. We have an equation that is the induction equation, how the magnetic field changes with respect to time, and in fluid dynamics we have continuity equation also. Now you just do a simple dimensional analysis. So if you have the continuity equation and if you do the dimensional analysis, you will turn up with this equation VI L equals to D0 L. That means the two plasma is coming towards each other with a velocity VI, carrying a magnetic field, same magnetic field. For simplicity, we are taking the same magnetic field, but opposite in orientation, obviously. And after reconnection or whatever is happening inside, all the plasma are getting out as an outflow with velocity V0, and the length scale is given by capital L. That is the length of this region, and small l is the width of the region. Then, if you do the dimensional analysis, you will get down to this simple dimensional form. And now you take the induction equation that we have told, and we are stating as a steady state, right? The steady state, del V del T has to be 0. No magnetic field changing is happening. If you do that, and same, you do the dimensional analysis, you will come out to this equation. We will use these two equations further. And now, the one point you have to keep in mind, that whatever plasma is coming inside, right? The same plasma will go outside. And what is happening inside? The magnetic field is vanishing at a certain distance. It is annihilating, right? And the magnetic field, magnetic energy, it is dissipated to kinetic energies. So whatever kinetic energy we are getting from the outflows, this energy is given by the magnetic fields, the annihilated magnetic fields. So you compare the magnetic energy density with respect to the kinetic energy density. And if you use these two equations, you will come up that the outflow velocity is actually the Alfvén velocity. Now you can ask me, what is Alfvén velocity? Okay, if you have a magnetic field, if you have some disturbance in a magnetic field, then that disturbance flows with the velocity. It's called Alfvén velocity. This is a very general definition. So we are finding out that this outflow velocity is Alfvén velocity. And now what I told you, the main important topic for us is reconnection rate, because different models have not produced the reconnection rate we want, the observation want. Like Sweet-Parker model didn't actually explain that. So what is the reconnection rate? You just divide the inflow velocity by outflow velocity to give a quantity called reconnection rate. Means by this quantity we measure the reconnection rate, how fast it is happening. So by this process, you will come out by just a basic dimension analysis. You come out with a reconnection rate expression, and you just calculate it. And you will find out, okay, it is matching with the observation or not. But unfortunately, Sweet and Parker model, that is this model, they have just simply took the dimension analysis and calculated the reconnection rate. This reconnection rate has failed to cope up with the observational data. In the solar case, the flares, these are happening very fast, and this reconnection rate was unable to explain that. It was very slow by the theoretical model, but actually it is happening very fast. So now there are other magnetohydrodynamic models that I'm not going to deal with, because my only intention was to just give a flavor how we can approach this reconnection problem with some equations, right? So we have done a part with hydrodynamic or magnetohydrodynamic or fluid approximation. So this is a fluid model where we have some flows coming to each other and flows going outside, right? We have not bothered about electrons and ions themselves. Now we are going deep into that. So there is a model called kinetic model or two fluid model from Biscamp. I think you might remember in that historical chart, the last point was Biscamp, 1995. He came out that, okay, that's fine. We are dealing with the magnetohydrodynamics, fluid scale analysis, but these are unable to produce the exact result, unable to produce the reconnection rate we wanted. So we have to go deeper into that. He proposed a further fundamental model called the kinetic scale model of reconnection. Here, what happens is we have to deal with the electrons and ions individually, not as a same system. So what is happening? Let's grab up everything in a short. So we have two fluids that have two magnetic field lines oppositely oriented. They're coming close to each other. And I have told you, in between that boundary, there should be a current sheet. That is a Maxwell's equation telling curl of P equal to mu naught J, right? And you have to push the two fluids so close that the sheet one time cross the threshold and it will tear up, right? Now, how long you have to push? This model will tell you how long you have to push. So before that's just describing this bizarre diagram, don't bother about that. It's very complex, but I will explain you very simply. I'll just want to tell you two fundamental things. You keep it in mind. Like we have all studied in MSc and BSc, like if we have a conducting medium and electromagnetic wave is flowing into that, there is a skin depth concept, right? The skin depth is a depth in that medium after which the intensity of the electric and magnetic field diminishes by 1 over E, right? So this plasma is also conducting medium. It has a conductivity. The ideal plasma, we used to say it's a highly conducting medium, right? It is actually a conducting medium. And the magnetic field, electric field, whatever dynamics we are studying, it is the electromagnetic field dynamics in a conducting medium problem. The same we have studied in MSc. So similar way, here we also have two skin depths, one with respect to ions, one with respect to electrons. So what we are doing in the initial position, two fluids, two magnetic fields, we are pushing further. Means we are not pushing, the system itself has a push between pushing the two systems into each other. That we have already seen in the video of magnetic reconnection at the magnetosphere, right? So once you push that magnetic field inside, if the magnetic field crosses the ion skin depth, then what happens? The ions are getting decoupled from the magnetic fields. They are not able to see the magnetic fields. Like they are totally decoupled. Their motion are not directed by the magnetic fields. That is called the ion skin depth. So this larger box that I have drawn in the red is the ion skin depth region. Means once this magnetic field or plasma, whatever, they crosses this region, then the ions are totally out of control of magnetic field. They do not know what magnetic field is. They are moving by their own. If some electric field is there, that will guide them. That is why these ions, if you see that four corners, they are getting deviated from the inflow region to outflow region because of reconnection physics. There are different other forces also that takes this ion from the inflow to the outflows, because obviously it has to go from the outflows at last. So it cannot cross this big box. Ions cannot cross because they are now decoupled, and because of some other forces, it straight away goes to the outflow region. Now, the electrons are only coupled with the fields. Ions are not. Now, you are pushing it further. Then what happens? As another region will come, another length will come, when the electrons are also decoupled from the magnetic fields. Then the full plasma is actually decoupled from the magnetic field. First the ions and then the electrons. This little box in the middle means given by the black box. After that, the magnetic fields are actually free of the plasma. And then field lines can reconnect, they can disconnect, they can reorient, whatever you can say, reconnecting, disconnecting, reorientation, whatever you want to say. That happens inside that box because the field line now is not controlled by the flows, not controlled by the plasma. All the electrons and ions get decoupled. And this region is called electron diffusion region. The outer region is called ion diffusion region because the magnetic field is diffused from the ion scale. The inner boundary, the magnetic fields are diffused from the electron scale. This is called electron diffusion regions. So whatever is happening inside, reorientation, magnetic energy is coming up and forming, means channelizing into plasma kinetic energies, acceleration is happening here only. After that, whatever happens, yeah. Yes.
Can you? We have time limit is there, so we can maybe go a little fast.
5 minutes.
Yeah, sure.
Yeah. Thank you for reminding. So whatever is happening, the reconnection, reorientation, plasma, magnetic field that is coming, that is actually giving rise to the plasma flows and accelerations. Everything is happening in this region. And after that, these electrons and ions are coming out as a plasma outflows. And once it is coming out, you see the magnetic fields are highly bent because these two blue lines are getting reconnected and they are highly bent at the outflow and they go with the plasma. And once you have bent magnetic fields, there are lots of energies in it, potential energy stored at a magnetic tension. And that magnetic tension, what it will do, the magnetic field will try to dissipate the energy. And that also creates some dissipations. It tries to come up with the normal potential state. So because of this highly twisted magnetic field in the outflow, when it goes through the outflow, it also dissipates the energy in the form of particle accelerations and other forms of energies. So this is the basic kinetic scale picture of magnetic reconnection. Now, my research is on magnetospheric reconnection. As I have told you, in the day side and night side, there are two reconnection scales, two reconnection regions. And you want to know what is the dimension of these two regions, IDR and EDR. In case of magnetosphere, it is huge. Our magnetosphere is like 10 RE, 10 into 6,371 kilometers at the day side. At the night side, it is 100 into RE. It is huge system. And these two regions where reconnection happens, this is around 10 kilometers. Is so small. So you can imagine if we want to track or trace or observe in our magnetosphere, you have to go that scale to this huge system. You have to trace this small scale. In case of day side also, in case of night side also. So these are the few length scale I have mentioned. In case of day side, it is of tens of kilometers. In night side, it's of hundreds of kilometers. So you have to go to this small scale to study what actually happening to the field lines, where the energies are going to channelize. Is it possible? In the next question comes, is it possible to observe? Okay, we cannot go to the sun to observe the reconnection. Sun, it is a very common case. In solar atmosphere, it is happening every time. And you know, one of the main challenging questions, that is a coronal heating problem, one of the contender is reconnection. And simply we cannot go to the sun and observe this reconnection problem. But we have reached up to the magnetosphere. Means we have reached in the magnetosphere, we can experiment in that. And many satellites from the space era have actually observed this reconnection phenomenon. And once it is observed and once it has some mathematical model, people actually accepted this model. In 2015, NASA came up with a dedicated reconnection observing satellite system or mission called magnetospheric multiscale mission. Now it is 2025, it is the 10 years of that. It is actually observing at the day side as well as the night side. It's not simultaneously. In a year, certain amount of months it will cross the day side and certain amount of months it will be in the night side. And it will study only the reconnection process. Why it is important to study that? The next question comes. Why it is important to study? Because, first of all, this process can lead to explosive plasma events. Explosively, it can give rise to energies. Even up to relativistic speeds, it can accelerate the charged particles in case of Sun, in case of Earth also. So that is a one fundamental question. Means fundamental physics, you are interested, you can study that. Number two, the coupling of solar wind energy or solar energy to the ionosphere, magnetosphere, ionosphere, even our Earth atmosphere. This coupling is actually based on this reconnection process. Whenever these field lines are opening up, the particles can enter into our magnetosphere system. Energy can enter into our magnetosphere system and it can enrich, it can affect everything, ionosphere, atmosphere, everything. So in that perspective, what is called space weather perspective, it is very important to study. So that is a MMS satellite, magnetospheric multiscale. Now we are actually celebrating the 10th year of that. And it is a formation flight. It has 4 satellites identically made. And is actually going into the small scale of 10 kilometers. This is a remarkable achievement by NASA and human being, so to say, in general. So what it does, as I have told, there are phases, scientific phases that are all over. Phase 1, phase 2, now it's in a phase 8 or phase 9 something. In some phases, they actually observe the day side. In some phases, they observe the night side. And they actually try to see how these charged particles are coming out. What are the velocity distributions for that? What are the energies for that? So we can identify the reconnection events. How we can identify? One example I have given here. You see, this is the day side reconnection event. And you don't need to bother about the plots. Only you see the E and F. This is the time series of ion velocity and electron velocity. So the MMS satellite, it was in the magnetosphere first, as in the bar, and then crossed the magnetosheath and came back again. The front part, I tell you first, this front boundary layer, it is called a magnetopause. It is actually separating the magnetospheric plasma and the solar wind plasma. And here itself, the reconnection happens. So it was going from the inside and outside and then coming back again. What it observed that I have to point out. You see, the background in the magnetosphere, the velocity was so low, and suddenly there is a jump, 0 to 300 kilometers per second. This is what called the reconnection outflows that I have drawn here. These are the outflows. We can see because of this formation flying, multiple satellites, 4 satellites coming together in a 10-kilometer separation. You can actually detect these outflows. These are called ion outflows. And even in electrons also, we get these outflows. And this electron outflow, this is 1,500 kilometers per second. Compared to the background, it is huge. So this sort of signatures will tell us that, okay, in the first hand, there can be reconnection events. Now, there are other checks you have to do simultaneously to actually say that, okay, this is a reconnection event. And what we usually do, we have all the parameters in a stack plot we use to produce these stack plots. And based on these identifying criteria like magnetic fields, energies, velocities, we try to construct a reconnection geometry. That is our job. That is my job to do. That is my research. We have to take care of reconnection events in the day side of the magnetosphere. How it is happening. We just plot it and see whatever signatures we are getting and try to draw up this picture. And then we do all the research things. Like it can be a broad research, it can be a small scale phenomena like instabilities, waves, etc., etc. Okay, so this is a basic thing I am doing currently, and this is a thing this missions, this dedicated missions for reconnection is giving us. So that's all for today. But I want to stop with saying that why it is important to study. First of all, I told you 3-4 reasons. One reason is because it's a fundamental physics phenomena. And we are interested in fundamental physics as well as space weather related things and the charge particle acceleration. This is a very important point. And people are actually interested in charge particle acceleration, how efficiently we can accelerate charge particles. And I have just given you example for Earth. In case of Sun, it is happening. In case of astrophysical settings, like magnetars, like black holes, there are papers. In black holes, accretion disk, there are reconnections, and charge particle can accelerate very promptly. So in that fashion, in that scenario, this fundamental process is very important to study. And if you go deep into that, lots of open areas are still left to cover. So if people are interested, you can dig into that. Thank you.
Thank you, Shibotosh, on a wonderful talk on the magnetic reconnection and its intricacies. Now this time for questions. Audience can ask their questions to him.
Yeah.
Hello, sir.
Yeah.
Hello. Sir, myself Shobhadro. It's a good talk. Sir, one thing I have a question. In your diagram, Biscamp model, when if we consider that two sides of plasma coming to each other, we see that
Right.
one in top of the part, the outer jet flows into space. I mean, if we consider the sun case, but what happened in the bottom case? The jet push the surface, then it will. It is I think it's a chain reaction. Then it will again push the sides of other plasmas. Then again it will trigger the outflows, and again it will.
Outflows and
It's a
reconnection again.
continuous.
Yes.
So it doesn't it make the surface of sun very unstable, and as a whole sun is
Right.
unstable. So I mean,
Yes.
being sun is a stable thing. That if the surface is so unstable, so this is my question. I mean, how it makes sense.
Okay. Sun is a stable thing. You means in what perspective you are saying? If you see the atmosphere of sun, means I do not have that much expertise in solar atmospheres and corona and photosphere, but I can say that this solar atmosphere, it is very, very unstable. You can see this kind of pictures, that bottom picture, every time, whenever sun is very active, even in case of, you know that there are 11-year cycle activity. Whenever sun is active, every time you can see these kind of flares coming from the surface and going inside again. Sometimes it can be disconnected also. So in that sense, sun's surface is not at all in a stable state. It is continuously changing. And as you correctly pointed out, this can happen continuously. If the condition prevails, it can happen continuously. And what about the outflows? One outflow, if you see, this is a reconnection point, right? One outflow is going outside. That has a sufficient energy, it can produce, that I told you, right? It can produce a chunk of solar mass, it can come out. And this we generally call CMU. It has to be a huge explosion. And the other outflow, it will come down to the solar surface again. This is called post-eruption arcade. So this is the two outflows. One is coming out of the sun and one is going down to the surface again. So actually the sun surface is not at all stable. It is continuously changing. It's very dynamic. I think it answers the question partly.
Yeah, sir. Thank you, sir.
Shibotosh, there's a question in the chat box from Devesh Bhattacharya.
Yeah.
Can MMS observe the temperature of the plasma as well? MMS.
Right. So what is the question exactly?
Right?
Sure. Yeah, right. So your question should be how we can observe the temperature of a plasma. That is very interesting. You have to know about kinetic theory of gas, right? You have all studied. There is a kinetic theory of plasma as well. If you know the distribution of the particles, from the distribution, we can actually calculate the temperature. That we used to do for kinetic theory of gas, right? If you have a Maxwellian distribution of particles, then we can calculate the temperature of that. The same way, this plasma is actually collisionless plasma. It doesn't follow Maxwellian. But if you have the distribution of plasma, actually this MMS is taking the particle counts. Actually, all the all the spacecraft, whatever is measuring electrons and ions, they're taking the counts with respect to energy beams, and they will construct the velocity distribution functions that we used to study in MSCs and BSCs, right? And once you figure out the distribution of the particles, you actually can calculate all the parameters like temperature, pressure, bulk velocity, everything. So yes, MMS is giving that thing also. These are called plasma moments data, means plasma moments. Once you have the distribution, you can calculate everything, all the moments of the system.
Basically, from the particle counts, you will get all the things.
Right. Yes. Right.
Hello.
Yeah.
Yes, Neela.
Yes. So I have two questions. So
sure.
at last you shown the MMS observations. So
Right.
you shown the magnetic field and the ions like ion
Yes.
states and the electron. So like particularly like how much time you're showing here that the magnetic reconnection and the like that there is shorter time for electrons, maybe it has higher velocity, maybe what is
Yes.
the relation? This is the first question.
Relation for
Like here we can see the time period of that reconnection. Yes.
yeah. Right.
And also you told about the Sweet-Parker reconnection rate equation, and it cannot
Yes.
do that. But after that you talked about kinetic scale, whether we
Right.
are able to do, like we are able to derive the reconnection rate based on this kinetic scale model, like that. Like I have
Yes.
this
Yeah.
question.
Okay. So first of all, this example that I have shown you, it's a minute scale observation. Like, see, this is 9/450 to 96, just a 1 minute and about that. So you see, this MMS is actually tracing the magnetosphere is like that. It is an elliptical path, right? So whenever it's going to the magnetopause, it is going crossing the magnetopause and coming back again. And magnetopause is not a stable boundary; it actually oscillates because the solar wind constantly pushing the magnetosphere, actually constantly interacting with the magnetosphere. So once you go to the boundary layer, you can actually detect the flapping of this boundary. It can come out and go in, come out and go in. This kind of thing happens. So, and these reconnections are very fast processes, and what we are measuring, it's a point observation, right? If my MMS is crossing reconnection, then only we can measure this phenomena. Otherwise, if misses, then you can miss it. So in this particular example, we have between 1 minute scale, we have observed ion flows, and you can see there are 2 ion jets. How can it be 2 ion jets? We are not simultaneously can process upper ion jet and lower ion jet. It is not like that. The MMS has crossed the magnetopause. In that time, magnetopause has shifted, is coming, there is an oscillation kind of motion. That is why when going time and coming back time also, there are 2 observations of ion jets. And in case of electrons, yeah, obviously, yes, electrons also have, in specific, in this, if you just see the diagram of that, there are specific regions, it's called separator regions of reconnected and not reconnected lines. I have not gone into the detail. In that separator regions, electrons can actually flow very fast, and that was detected here. So that is the first question, first answer of your question. Okay. And second one, can you just repeat once more? Yeah, rate, reconnection rate. Yes.
Yes.
So
Yes.
based on this kinetic scale model, and there are some statistical analysis for that, because it's already 10 years of data we have, and not only MMS. Before that, there are cluster missions, there are geothermal missions that also have gone through reconnection observations. So people have done that, like using this kinetic scale theory and observations, they have derived the reconnection rate. One way I have told you that you just calculate VI and V0, inflow and outflow velocity. But observation, you cannot simultaneously trace inflow and outflow velocities.
Yes.
And how can you do that? There is a way. In the diffusion region, there is no magnetic field. Magnetic field is blowing up. It's going to 0, right? They're reconnecting, disconnecting, reconnecting, right? That is why your magnetic energy is coming up to kinetic energies, because magnetic energy is not there. Magnetic field is not there. Here comes electric fields. There is something called reconnection electric field inside that. So whenever this magnetic field is going to 0, there is a reconnection electric field. That electric field comes because of these particle motions. Their electrons and ions are behaving differently in kinetic space. That will lead to electric fields. So this MMS can actually observe these electric fields. It can catch the electric field. It has electric field probes. So once you have the electric field measurement, so this electric field is a proxy for measuring the reconnection rate. And yes, people have done that. They have calculated this electric field from this diffusion region observations. And that is one more important thing. Every time you cannot trace the diffusion region because it is a point means if it is tracking, then it is tracking, otherwise not. You can miss it also. Whenever there is a diffusion region observation, people have done this reconnection electric field measurement. And from that electric field gives a proxy of reconnection rate. And yes, the answer is yes. They have statistically, they have shown that by this amount of observations, it is actually very fast. That is not following the Sweet-Parker rule. Sweet-Parker rate reconnection is actually very fast. And that actually this ratio VI by V0 is around 0.1. Is the inflow velocity should be 0.1 times the outgoing velocity. That is usually we used to take it. That is a fast reconnection rate.
So here, in this figure, this is the observed electric field you're talking about, the second
So,
last minute.
No, in this figure we actually not observing this inside box because we are just touching the box and coming out. So we do not have any idea what is the electric field in between the box. That is a diffusion region. So in this particular example, we cannot do that. But there are observations that this spacecraft has tracked this inside region also. Then you can have the electric field measurement. And by that, you can tell that, okay, this electric field is this much, so my reconnection rate is this one, because this is a proxy for that. Okay?
Okay, thank you very much. Yeah, it was great talk. Thank you. Thank you.
Hello. Shibotosh.
Yeah.
It's a nice presentation. I have some doubts. Like you told about skin depth.
Yes.
How you are connecting the skin depth in the conducting sphere, where the charges resides on the surface and in a plasma, and whether the equations are same or some more information has to be added in the case of plasma.
There has to be some more information, but means in general, you can think of the plasma system as a conducting system because plasma has free electrons and ions, they are moving, right? So they can sustain currents. This is a conducting system. So once you have a conducting system and you have some electric field, magnetic fields, then you can use that concept of skin depth. Like you can, this is just like a similar analogy for that. Okay, so that is what actually happening. If you go deep inside that, and once you cross this specific length scale, then electrons, ions first decouple, then electrons are decoupled. So it's just like an analogy what I have given to track you better in a better way.
And you told about changing of magnetic field of the sun, I think, in the very first thing.
Yes.
So when the polarity it changes, right? So is there any like northward or southward, like you told, right?
No, in case of sun, it is not happening. In case of Earth, it is.
No, means whatever the plasma is coming through the solar wind, that magnetic, and how it is connected.
That is a different magnetic field. That is called Parker spiral. That is different. That is not coming from the reconnection. That is not the connection case. Yeah.
No,
I have given one example. That is a flare case. That is a typical one example. Even without flare, also reconnections can happen, and reconnection can give rise to heat and energies. But in case of flare model, that is the usual first-hand model for that. Whenever reconnection is happening, that gives rise to electromagnetic fields, and sometimes to the CME ejections and so on. That interplanetary magnetic field, that is not coming from there.
No, I heard just query about how fast it changes the direction, means if it is changing.
Okay, that depends on the situation, right? In case of active sun period, it can change very fast. And if you can observe from L1 points, there are lots of spacecraft now, even India also has. You can observe the magnetic field orientation, it changes, it has the fluctuations. from positive to negative and so on. And there are lots of structures like current sheets, like heliospheric current sheets and so on. Everything is there. It can actually change. It's a dynamic process.
Okay. Means any number, can you tell? Or
Number, no, not now.
Okay.
I'm not remembering things. Yeah, I'll tell you once I.
Okay. Okay.
Yeah.
Okay. Thank you. It's a nice presentation.
Thank you.
Is there any more questions? Okay, if there are no more questions, we can wind up. Shibotosh, thank you once again for the
Thank
wonderful talk,
you.
and all the best for the your further research on this magnetic
Thank you.
reconnection. Okay, thank you.